Good morning. Welcome to Krishna's classroom. With the objective of looking at the Banach theorem and understanding it geometrically, we had been considering the concept of linear functions. And now what we want to do is we want to look at what are called normed linear functions. So we have to introduce the concept of norm on linear functions. The linear functions are essentially linear transformations from one vector space into another. That is clear. So we can talk about the norm of that. Once your basic spaces are normed spaces, then it induces a natural norm on the linear function. So we are going to analyze that, but how it is related with the geometry. Of course, one of the things that we have been doing is exploring the geometry of linear functions. Now let us put the whole analysis, whatever we have done so far on this, into a more formal form. So X is a linear space over K. K stands for R or C. If it is the associated field is R, then we call it the real linear space, or if it is C, then we say it's a complex linear space. Now F from X to K is a linear map. So let we call this, and you know that X is a linear space, K is also a linear space, so it's a linear map from one linear space into another, therefore it's a linear transformation. Okay, so that's the status of. So linear transformations from the vector space to the associated field are normally called linear functions. Now we assume, okay, so we look at the null space of if F is a zero linear function, then null space of F is X itself. This is a trivial scenario, and this is trivial. This is a So we shall consider the non-trivial case of f not equal to 0. Now f not equal to 0, so f is a map from x to k. F is not equal to 0, that is, there exists some vector such that is not equal. What's the meaning? Now we have the following theorem. The null space of F is a maximal proper subspace of X. Null space of F is a maximal proper subspace of X. Whenever so we shall quickly give a proof of that, formula of that. So F not equal to 0 implies there exists y not equal to 0 such that Fy y not equal to 0 such that Fy is not. Now we shall first prove that show that for any there exists a unique X prime belonging to the null space of F, that is for and a scalar k k1. So that is the first thing that we show. Okay. So if such a the problem is to determine k and X prime with this property. So let us do that. If such a suppose, then we should have fx equal to f of x prime plus a times y. Because f is linear. Now the problem is, can you determine a k with this property? Okay. We shall just see whether we can determine a k with this property. Now, choose equal to 0. That is now fy is not equal to 0. Hence, we have k determined by fy. Okay. X equal to so this is the breakup. So we take k by this one. So this is the, so this belongs to, so we write x equal to plus and x prime belongs to this case of. So that is a breakup, and this is unique. I mean, you can show that this is unique. Now this is easy because you take, suppose you have another representation, x equal to x double prime. Suppose x, there exists another representation, x equal to x double prime plus some k prime y, then you have x is also equal to x prime plus k y. Now, so you see that 0 equal to x double prime minus x prime minus k y. Okay. Now, you see that you apply f on this. Now, this is in the null space of f, therefore this is 0. So, you get k prime minus k. Okay, so you get k prime minus k. K prime. So once you get k prime equal to k, then from this it is easily verified that so that is the quick proof of that. If it is not equal to 0, then NF, which is a subspace, which is not equal to x. It's a proper subspace of that, and span of x is equal to so you take this NF and y and then take the linear combination. So any x can be written as a uniquely determined element and a scalar multiple. Both in the scalar and the and the element in NF are uniquely. So the question is, okay, so remark, note that NF maximal NF is a maximal proper so that's one of the remarks that we want. Now the question that you ask is this. So apparently NF and this K have a connection with F. So once F is given, F associated with F, you have NF and the scalar K. These two essentially is something that comes out of F in this following way. So our question is this. Suppose M is a maximal proper subspace of X, by which you mean that x is equal to span of y naught in M. It's also called a the other terminology is that, okay, I'll make a note about it. Or is it something, or does there exist an f, a linear function on x, f not equal to 0, such that nf is equal to m? Okay, right? So this is the question that you ask. Now let us immediately see the following. Note that if f is a linear function, alpha f is also a linear function. Alpha not equal to 0. Even when alpha equal to 0, it becomes a 0 linear. Okay. Then the null space of that is, if G is null space of G. So the answer to our question is that you don't have uniqueness. But now how to make this unique? It can be made unique by choosing a vector y which is not in the space, as well as a appropriate scalar. Okay, scalar value k. Right. So you see that x belonging to can be written as x prime plus x minus x prime, where x prime belongs to M. And now x minus x prime, unless x is equal to x prime, x minus x prime does not belong to it. And M is so we shall now define a linear function by what is it? X equal to x prime plus some ky, where y does not belong to M, and k belongs to scalar. K is a scalar. F of x prime is 0. So assign a value for y. Then null space. Okay. So given a maximal proper subspace, it is also called a hyper space. The maximal proper So whenever we use the word hyperspace, means a maximal proper subspace. That means the codimension of that subspace is equal. Okay, so that's the meaning of that. A hyperspace Y which does not belong to M and alpha. A unique linear functional f on x such that f of for x belonging to M and f of equal. So this is a unique linear function. So unless you fix this value also, you are not going to get a unique. Sure, there are several linear functions because all scalar multiples of f also have the same null space. That's what. Now let us look at the following scenario. So let us go to R2. In R2, what are the proper subspaces of R2? Maximal proper subspace of R2 are lines passing through them. So this is here. In R2, maximal or hyperspaces are lines now let us choose a y which is not here. choose a vector y. This is yeah, y which does not belong to. Now look at the linear space spanned by. So this is the linear space spanned by. So y is not equal to 0. Now you see, you take any vector. Any vector. It's an arbitrary vector. And you know that it is the parallelogram law that works. So what you have is, complete a parallelogram. This is the vector. Now this let us resolve as a vector in M and a vector in this one. Okay. This is some ky. This is your x. And this is your x. So x prime is in M. Ky is in the space spanned by the vector y. And the next is a unique breakup of, or is written as a unique sum of x prime. For any x, there is a corresponding x prime and there is a corresponding k. So it varies from point to point. For instance, suppose you take your x somewhere here, then what you do is complete the parallelogram with M as one of the sides and the subspace bracket y as another side. Okay. So then you see that this is going to be k prime y and this is going to be x double. Okay. So if this is the x, then you are going to have x double prime plus k prime. So you can always resolve it, and this resolution is unique because you see that it's only when it is a parallelogram that these two vectors add up to give you. Okay. So the vector addition is a parallelogram law of addition in a vector space. That's important. And you want M to be the null space of F, which means that f of x prime has to be 0. And then f of x is equal to y x prime belongs to M. Okay, and K. So what you have to do is, if you want to get f of x and x prime is in M, you want f to be 0. So it is going to be f x prime plus k times fy, and that's equal to 0 plus fy, and fy is and so prescribe to fix. That is the we make an observation. So let us define the following space. M plus y will be defined by set of all x prime belongs to okay. So what is this? Then this is not a subspace. But it is a translate of M it's a translate of M to the vector. So in R2 this turns out to be a line parallel to M and passing through okay. That is the structure of M plus Y. And in R3, hyperspaces are planes through the origin. And M plus Y is a subspace, is a plane parallel to M and passing through passing through Y. Okay, so it's a translate of the parallel translate of the plane through the vector so you take, suppose this is the plane that passes through the origin, or this is the plane that passes through the origin, and this is a vector, then you translate this parallelly through the vector, so that is the plane, and this is not a subspace Y belongs to M, then this is a translate. I mean, it's M itself. Okay, if Y is not in M, then this is not M because it's a line, a plane that is parallel. Okay. Just a lot of lines up. This is called a fine. So here in R2 it is a line that is getting translated through the vector, whereas here it is a plane that is getting translated. So in general the structure is, suppose you are taking Rn, then a maximal proper subspace will be an n minus 1 dimensional subspace. So you take an n minus 1 dimensional subspace of M of Rn, take a vector Y which is not in M, and then look at M plus Y. M plus Y is nothing but a translate of the n minus 1 dimensional subspace through the vector. So that is the geometry of the problem. Okay, so every element of M plus Y is a vector in M plus the vector Y. Okay, so that's the picture that we have. Now let us designate by the form. So let us take. So what you do is you take a maximal proper subspace, namely a hyperspace in a vector space, and then do all these translations. Okay, so you get copies of this, but the translated ones are no more having the vector space property. So we can now construct a vector space called the quotient space. So define the following. That is y1 is related to y2 if m plus y1 equal to plus y2, which is equivalent to y1 minus. That is the definition. Okay. Now you observe that now note that it's an equivalence relation y. If y1 equal to y2, then y1 minus y2 is 0, which is in M. If y1 is related to y2, then y1 minus y2 belongs to M, which implies y2 minus y1 belongs to M because M is a subspace, and therefore y2 is related to y1. So it is symmetry. Similarly, you can show that if y1 is related to y2, y2 is related to y3, then y1 is related. Okay, so it's an equivalence relation, and therefore what does it do? It partitions namely so for each k you get one translate. Okay, note that if and only if k1 equal to k2. This is quite easy to. So what you have? You have the following property that partitions the union of results. Okay. So every x in x is in one of these m plus k1, and obviously every element of this is in x. So that's all. Okay. As we have already seen that this is union of this one. Now we shall introduce the concept of. So we just recall, when you take f not equal to 0, f a linear function, the null space of f is a hyperspace. And ky and y does not belong to this is a disjoint union. Now let us start looking at defining a norm. So what is a norm? Now assume norm union space. Okay. And we will use the notation the field K. What is it? That means there exists a map which is designated by this from equal to 0. And this is true for alpha belonging to one talks about the scalar, what happens when you take the scalar multiple and compute its norm, how is it related to the norm of x. The other one relates to, because you have the addition prop of is another operation that you have in the linear space. We are saying how it is going on the addition. Says that norm of x plus y is less than x plus norm. But this is the triangular linear. Okay. So suppose you have an f. Then we can define norm of f is defined this is the standard induced norm that you have on the class of linear functions f. Okay. Right? So what is it in this case? See, you have now we define on this so we set by taking f equal to 0, f of x equal to 0 for every x belonging to and of course what you have is this y such that y does not belong to M, and because it's an element of x, x is a non-trivial space equal to 1. Right? Now, x is equal to x prime plus a times where x prime belonging to M and k uniquely determined. Now define f of x equal to k. That means we are setting equal to 1. Okay. Now compute the norm. M plus y f of equal to 1 for every x belonging to x. Okay. Right. Norm of f equal to Hmm? See, fx equal to, and fy we are setting as 1, therefore that's why you get fx equal to. So what you get would be is equal to mod. Therefore, in this case, f takes the same value plus k. Namely, okay. So norm f would turn out to be supremum of and this would turn out to be simply 1. Okay, because for instance you take R2, take all lines. Now you see that for any x here, this corresponds to fx equal to 1. Okay, so this is and For any x here, this is m plus ky, and f of k, right? So on each of these, this is equal to 1. So you see that always when you take the absolute value of fx, that is going to be mod k, right? Therefore, mod k divided by norm x equal to 1 means if you take any x here on this, you see that the norm of so this is equal to, that is what the norm is all about. Okay, so we will now start interpreting the Banach theorem. So that will be our next class.